what is our formula, like I said before, that we use in a DC circuit to calculate wattage? Voltage times by amp. So that's our starting point for this. Okay. What else did I say that was going to cause an effect on this for when we have power in the circuit?
Resistance.
Resistance will do, but that's not what I'm looking for this.
Impedance.
Impedance will cause it. What's this thing here?
Yeah.
PF, the power factor. Our cosine now. Okay? So to work out our wattage, okay, it's voltage times by current times by cosine. Do you want me to put the equal sign in first? Well, and if you divide the whole formula by 1,000, it will give you it in kilowatts. Okay? Does that make sense so far? Okay? How do we work out the cosine?
So, yeah, there should be 180 degree in there. If that's 90, that's what kind that's all.
Oh yeah, that's always going to be 90 there.
Yeah.
Okay?
It's an equal Laplace.
There's an easier way of working it out. Come on, Mr. Maths teacher, how can we work out cosine? Okay, so our adjacent divided by the hypotenuse, to put that in terms of what we're looking at here, it will be have I written that the right way around? It's been a long day. Okay. So from that, we now get the formula of true power divided by apparent power equals our cosine. Okay? Or if you simplify it to symbols, it's kilowatts divided by kVA equals cos. Okay? One more thing to bear in mind from this is from that, we can actually calculate the angle of that triangle. So if we're drawing it to scale, you could measure it, couldn't you? Okay? The quicker way is to convert it, and we can do our angle. Okay? On your calculators, you've got a function called cos minus 1, and it will take the cosine, okay, and it will convert it into an angle. Okay? In a truly resistive circuit, our cosine would be 1, which would mean that the current and voltage are in sync with each other. Normally, if we've got an inductive circuit, we would have at least 0.8 for a cosine. Okay? So if you want to have a go at this function on your calculator, if you press shift cos to get the cos minus 1 and put 0.8 in there, I'm curious what you guys are cracking up at now.
So shift cos.
So press shift cos, and then put 0.8.
0.8.
We should end up with an angle.
Do you have to do it in brackets?
It should automatically kick the bracket off.
So
You
I've
don't
got,
have to close
I've
it.
got 36.86.
Yes, that's 36.86. You got 36? That's correct. Yeah, 36 is correct. Okay.
Okay, so shift cos.
You got 36, did you say? Yeah. That's correct. 36 is correct. 36.86, which is exactly the same. Okay?
Is
So,
this all about sizing an AC generator?
you can do it with AC generators, you can do it with motors, you can do it with fluorescent light fittings. Anything with an inductive load, you can start doing this on.
When you want to work out the power factor and the kVA.
Yep.
So if when you buy a cheap generator, it will say 3,000 kVA.
So that's the wattage, that's the total energy from that taking into consideration the reactive power. So that's the total apparent power. The true power is our kilowatts, what we're going to generate.
So that's what it can run.
That's what it can run.
But they're selling it, advertising it, saying it's the KVA. Okay.
That's it. Okay.
So a 3000 KVA generator probably going to run what? I don't know, 250 watts.
250 watts easily. Okay. Once you start taking off the reactive power in it, it starts to reduce it down. So it's going to generate that much, but it's going to have a loss on the reactive power, isn't it?
So it's going to use a lot of petrol.
Yep.
Yeah.
Okay. So that number you've calculated at the 36 degrees would be that if you'd drawn this as a triangle, that angle here would be 36 degrees. Okay, does that make sense? Okay, the smaller the angle we get, the more efficient the system is. Okay, does that all make sense so far? Okay.
James,
Yeah.
just explain reactive power again.
So-
Not what we in the sense of the data point thing, because I don't understand that. It doesn't come through to me. Just what is it just a resistance? So,
Remember when we had that coil of wire?
yeah.
Okay. We were generating a back feeder current, weren't we?
Yes.
A new form of resistance.
Every time we make a new winding.
Every time you run that current through there, it's
Yeah.
creating a current running in the opposite direction, isn't it? So it's a type of resistance.
Yeah.
So when you apply a current to a resistance, you end up with
Waste energy.
waste energy, don't
Yeah.
you? So that's what the reactive power is that wasted energy.
Yeah.
When you
Right.
run the current through that, it's going to create a waste.
Yeah.
That's what we've got to take into consideration. Okay?
Where did that 0.8 come from again?
That was just a random one I've given you off the
Oh,
top of my
okay,
head.
okay.
It's quite a common one that you tend to find with most inductive loads.
Yeah.
Is it's usually 0.8.
Right, okay.
Okay. So this last side here, reactive power is measured in kVAR. Okay? And the way in which we can calculate this is we go back to our Pythagoras' theorem now. Okay. Do take a picture of this. Okay? It lays out everything around this power all on one board. Okay? Okay. So the kVAR, that is our kilovolt amperes reactive, because it's a reaction of putting the AC current through that coil of wire, putting the AC current through a capacitor. It's that reactive power. Okay, does that make sense? Okay, everyone happy so far? Fantastic. It's worked out a lot better teaching off the whiteboard than it does using this. Okay, you've got these notes in front of you. Okay. It's exactly the same as what I've just been running through on the board, except I've given you the formulas with the sides of the triangles. Okay? Yes, I did select colour again, and for some reason it was printed black and white. They changed the photocopy system in the summer. Okay? So you can see the formulas that I've got on the board already. So, shall we start to put some maths into this formula for us, shall we? Okay. Right, are you all happy for me to rub some of this off so we can see where we're working with this triangle? Yeah. Fantastic. Okay, anyone not happy? Right, so we're going to start off with a particular inductive circuit produces 4 kilowatt of true power whilst producing 3 kVAR of reactive power. They've asked for us to calculate the apparent power and the power factor. Okay? So I always like referring back to triangle personally because it just makes me think of where everything needs to go. So my first point of call is I'm going to start putting the values onto this triangle. So on this question, what is my true power?
4 kilowatts.
4 kilowatts. Now they haven't given me my apparent power, so I'm not going to put anything down for that, but they have given me my kVAR.
3.
Oh, 3. So we can go back to Pythagoras' theorem for this to be able to work out the apparent power, because that's the first part that they've asked us to work out, haven't they? To work this out, we can do the very simple what we've done before. Kilowatts squared plus kVAR squared. Okay, you all happy with that? Now, because all the values are in kVA, you don't need to worry about putting the thousands in. You can just do 3 squared plus 4 squared equals. Okay, so if you want to put that into your calculators, so you can give me an answer. What did you get?
25.
25? Have you square rooted the formula?
I've got 5.
Should be 5.
It will be fine.
Yeah. If you square rooted the 25, you'll end up with 5. So 5 is what we're looking for on this.
Yeah, 3, 4, 5. 3, 4, 5.
It is the 3, 4, 5 method of remembering it. Okay. So how can I work out my cosine, my power factor? You look confused at the back there. Did you not? You look confused, yeah?
Power equal
You want me to calculate? What did you say?
we use the power formula.
So it'd be your kilowatt divided by your kVA.
Yeah. So it's going to be my kilowatt divided by my kVA, isn't it? Okay. So 4 kilowatt divided by
5. 0.8.
0.8. So that is my cosine. Okay. Has everyone managed to do that? You all happy with it so far? Anyone not happy? Anyone thinking they wish they became plumbers?
No, after today. I've been plumber, went straight through a water pipe and we had to turn the stopcock off.
Right.
Talk about that. I was in a rewire last week, and you know, plumbers normally cut and notch out the joist. Well, before they put the heat,
Are you all happy for me to rub this off the board?
the electricians, years and years and years ago,
That's the
cut and notch
cosine,
out
so that's the
cables,
power factor here.
Put fucking heating pipes on top of the cables. So they couldn't be bothered to fucking.
It doesn't really have an SI unit. You can put PF next to it,
Everything
but
still
it
works.
doesn't, it's not. It's just a power factor.
They don't make cables as they used to.
Fucking don't, mate. I tell you, they fucking don't.
Right, so I've put the next example on the board. Okay, so this one's working out in a lot more detail now. So are you all happy for me to rub this off the board? Fantastic.
Kettle used to boil in half of the time. James?
Sorry.
The kettle used to boil in half of the time. Thanks.
Right, so they want us to work out on this. A single phase AC machine. It draws 10.87 amps from a 230 volt supply. The power factor is 0.6 lagging. Okay? So I know that I can put 0.6 here. Because that's my power factor, isn't it? Okay? I can't put any other values on that triangle yet, can I? Because they've asked me to work out the apparent power, the true power, and the reactive power. Okay? So, who can remember from what I showed earlier, how are we going to work out our apparent power first? Not that one yet. Okay. What's it measured in? What's apparent power measured in?
Square root.
No, it's not measured in square root.
EVA.
kVA is what I'm hearing, isn't it? So it's measured in kVA. So if you remember, I said this one was in its name, wasn't it? So to work this out, I'm going to do voltage times by current divided by 1,000. Okay? So what's my voltage? 230. What's my current?
10.87.
And if I divide it by 1,000, so if you put that through your calculators,
2.5.
I get 2.5 kVA. Does everyone agree with that?
Yeah.
Everyone agree? Okay, so my true power now. Who can remember this one? You look at the picture that you took a few minutes ago, it might help you.
Kilowatts.
It's measured in kilowatts. What's the formula that we're going to use to calculate that? PF? PF's in it? So I've got my PF. What else have I got to put in this formula? Well, that is the PF, isn't it? That is the cosine.
You want kilowatt divided by kVA.
You guys go down the wrong line. So if you remember,
What are you after? The true power?
true power.
Yeah.
True power is equal to voltage times by current times by cosine. Okay, do you remember that when I drew it on the board earlier? So it's my power factor on my cosine times by my voltage times by my current will equal my kilowatt. Okay, so what's my power factor? 0.6. What's my voltage? 230 volts. What's my current?
10.87.
Okay. So when I multiply that all together, what do I get? 38.7, someone say? Just 38.7. I think that's slightly wrong.
On the paper it says 1.5 kilowatts.
That sounds better, because you're going to have to divide it by 1,000 to get it into kilowatts. Okay. So come on, let's put that through the calculators, please. Let's see what we get. Try it again. I think you might put a number wrong somewhere. Okay, accidents do happen.
Kilowatts.
1.5 kilowatts, that's perfect. The rule of thumb for this is because that's the shorter side of the triangle, it's got to be smaller than this, hasn't it? Okay? If we end up with the answer being bigger, we know we've done something wrong somewhere. Okay? So, the last thing it's asked us to work out is the reactive power. Okay? So to work out my reactive power, I'm going to do my apparent power, because that's the biggest, and I'm going to take my true power away from it. Okay? Okay, so if you put that through your calculators, you should hopefully
2 kilowatts amps or
anyone get an answer for this?
oh, error.
Well, error.
Yeah,